Hey guys, it's Ali, and in this video I'm going to be talking to you about 7 lessons I have learned from 7 electrical engineering internships at multiple companies that I have worked at. And if you're wondering why I've done 7 electrical engineering internships, why so many, it's because I've done these throughout my bachelor's, master's, and PhD. I've been in electrical engineering for over 8 years, and I'm basically finishing up the PhD. I've done all 3 degrees, and basically what I plan on doing over here is to go through the 7 lessons from each internship. For each one of these internships, I want to talk to you about what the internship was like, what I worked on, what my experience was, obviously the lessons that I learned, and then towards the end of the video I'm going to be talking in a lot more detail at the end of each internship, as well as at the end of the video I'm going to talk a lot about what you can do to increase the odds of getting an internship, whether you're an electrical engineer, mechanical engineer, software engineer, or anybody who's interested in technology or college student in general. So the way I plan on doing this is to just basically go briefly through one by one, and I'm basically just going to reference my LinkedIn profile here, because on my LinkedIn profile I have, and on my resume as well, I have bullets that I'm going to also use this video as an opportunity to show you how I set up my LinkedIn profile and how I set up my resume as well, and how I talk about my internships. So as you can see over here, the internships I have laid out in my LinkedIn profile, it's very brief. I don't really like to go too much in detail. Like, I just basically talk about the main topic that I got to work on. However, the thing is, in my CV or in my resume, I like to actually go a lot more in detail, and I like to have at least 3 bullets discussing what I did. So I'm going to start with the very first one. I'm going to go all the way back from my very first undergraduate internship, which actually was at Northrop Grumman Space Systems. So this was over here. This was back when I was I think a junior in college. Junior going into my senior year, and I worked at this company called Northrop Grumman. And basically my project was to do a link budget analysis and on-orbit troubleshooting for millimeter wave satellite communication systems. Now, what does that even mean? So basically, I was working on a satellite, and the satellite looked like this. It was called Advanced EHF, and as you can see over here, it's pretty intense. It's a pretty complicated satellite that has tons of antennas on it. These are a bunch of arrays. However, as you can see, there's this dish over here, and I was basically working on this dish. This was called the crosslink subsystem, and I basically was tasked to basically do something called a link budget. And a link budget in communication systems is just basically like power, like here, I could probably explain this. Link budget, communication systems. Basically, you have, here, let me see if I can find a better explanation. Yeah, so that's probably a better way to do it. So you have some ground stations on the Earth. Now these are antennas that transmit electromagnetic waves talking to the satellite. Uplink is the ground station going to the satellite, and the satellite going down to this ground station. And a link budget is basically just the budget of power that's basically going from one antenna to the other. So when you're transmitting power here, just like with water, picture yourself like you have like a hose of water, and you're basically shooting water. At some point, the pressure of the water is only going to push it so far, and it's going to start like kind of weakening. You can think of a similar analogy for electromagnetic waves, where as distance, the waves travel over distance, the waves start spreading, so you start losing power, and your signal becomes weaker and weaker. So by the time the signal leaves the ground station and gets to the satellite, it would become much weaker. And basically, I basically had to do that, and I basically developed a tool that would predict what the signal would be. So if we have a satellite, so again, going back to the advanced CHF signal, crosslink. Let's hope there's a picture with the 2 satellites. There is not, but let's say 2 satellites, crosslink. I really want you guys to visualize what is happening. So if we have 2, let's say over here, like there's 2 satellites over here in the same orbit, and this guy are responsible for talking to each other. My job was basically to predict how much signal strength will be arriving between them, and use that basically to troubleshoot anything that is going on that could go wrong. This obviously forced me also to study the on-orbit performance, and this was really cool because I gained system-level experience for millimeter wave communication. Now, millimeter wave, basically it's a band within communication. You guys might be familiar with 5G, so like 5G, like the core networks, or like here, 5G. So the whole idea behind 5G is that you're going higher up in the electromagnetic spectrum. So let's see, 5G frequency band. And yep, I think this is exactly what we're looking for. So here in the millimeter waves, we're actually going higher up in frequency. We're going to like tens of gigahertz. Now what that allows us to do is we're going to tens of gigahertz in frequency, which means in bandwidth. We get to increase our signal bandwidth, and because we increase our signal bandwidth, we get to increase our data rates. So basically the amount of information we're able to send in space. If all this stuff is like really scaring you and confusing you, don't worry. If you were to take communication systems, you would basically learn a lot about this stuff. Now the cool thing I got from this internship over here was I learned a very valuable lesson. This was my very first ever internship, and because it was my very first internship, I didn't really know what I was doing, and I asked a lot of questions to a lot of people. Luckily, I had a really good team of people, of other engineers who were full-time, that I could go to for all sorts of questions. And this was when I was reading a lot of books by Richard Feynman, and I don't know if you guys know who that is, but Richard Feynman, he was a Nobel Prize physicist, and he was notorious about the idea of like ask stupid questions, like don't be afraid of looking stupid, because it was my very first internship. I was very concerned that, oh my god, I have to look smart, and I have to look like I know what I'm doing, and I have to look like I know what I'm talking about. And I think I tried that in the first few weeks, and it was totally the wrong approach. I was too afraid to ask any questions and things of that nature, and I got nowhere. And only when I started asking other engineers around me for help did I actually start learning and start understanding what to do. And also another thing, there were a few things that I did in that internship that were really, really well, that were good, and that on top of working on my project, I basically attended a lot of events that the company was hosting, and I would go and talk to a lot of engineers, and I met with a lot of engineers who were working in other departments, and I would see what they were doing. And at the time, Northrop Grumman was building this James Webb telescope. You guys probably might know what that is. A very famous, very expensive telescope that is in orbit right now. I believe it's like between Earth and Mars, and it is basically taking pictures of really, really, really far away light, and it's trying to understand like how the galaxy was formed. And basically, it's like the Hubble Space Telescope on steroids, like a lot more accurate with much higher resolution. I mean, it's made of all these different panels that are integrated together. It's a really, really cool project. And I met a few people at the time who were working on this, and through meeting them and talking to them, I got to learn like some really, really, really cool stuff. So that was pretty much it for my first internship. Now, right after that, I went into my first NASA internship, which, man, that was so cool. That was at the NASA Kennedy Space Center. This was an integration building. Is very famous. This is what the visitor complex looked like. I actually even remember bringing my family over, my parents, to this visitor center. This was really, really, really cool stuff. And over there, when I was there, I was working on. Actually, I think I still have the paper. So Alqaraghuli, NASA, hardware in the loop. Oh, there it is. Cool. Yeah, so it's actually quite nice. So I have this, my project is right there. It's documented. It's on the NASA website. And what I was basically working on is I was developing the title of my project was called, or in this case this paper, Implementation of Real-Time Hardware-in-the-Loop Simulation for Wave Instrument Avionics. So basically what I was trying to do at the NASA Kennedy Space Center, I was trying to emulate and simulate the performance of hardware that would be equipped on a moon rover, but basically, instead of trying to have all the components out there, we wanted to replace them with a bunch of resistors and test out how the hardware would look like. So that internship involved multiple things. It involved software, and it involved hardware, and it involved like circuit design, as well as involved printed circuit board design. And like, for example, these were some of the breakout boards I designed initially. This was the stack, the hardware stack architecture, how all the different components, basically the different organs that were controlling the brain of the vehicle, and then some circuit simulation as well. And we were again using resistors just to simulate some of the loads, and like these are some of the calculations that derive them. And man, this project was super cool, mostly because it involved. I mean, I did this 2017. That was what, like, oh my god, like 8 years ago, and I think I was only, oh my god, I think I was only like 18 or 19 years old at the time, or I don't know. Yeah, I was very young, but it was so cool because I basically worked with 8 other NASA engineers, and I was doing so many different things. I was doing even some technician work, like some breaking down, like cutting some wires and making connectors. I was doing some software. I was doing some printed circuit board design. And printed circuit board design, or PCB design, is really cool. I was using this software called Altium, basically to basically build these boards where the components would sit on, and then they would get soldered by the technicians. And it's actually super cool because you get to place components, and then you get to like connect them through traces. Like for example, in this case, there's a capacitor, and as you can see, this red here, there's like a trace. It's like a piece of metal that's connecting them, and then there are requirements for like how thick or how thin they need to be. And it's really cool because it's like at the interface of electrical and mechanical engineering, because like there are electrical requirements, but then there's also like thermal requirements. Like for example, the trace has to be wide enough, like in case it heats up, or in the case, I mean, all these were DC circuits, but in the case of like if it was RF or microwave circuits, then they would need to be like the right length or the right configuration, so that way you would be able to have the circuits being matched. And that was really cool. And I learned many lessons in this internship, and I think I still actually have I think I have a picture from that internship somewhere. Yeah, I can't find it. But basically, from this internship at the NASA Kennedy Space Center, and actually, let me take a quick look at my resume here. So again, I worked on analog circuits. I developed the hardware in the loop test, and the hardware in the loop test is, again, we're just basically placing resistors for loads, and we're running the test to see what would actually happen as if it were in space. So we're taking the entire like hardware architecture, we're emulating the loads, basically the devices with resistors, and we're running the software and we're seeing what actually happens. This would allow us, and on top of that, I was also like, I had a really cool mentor at the time, and on top of being able to work on my main project, I was also troubleshooting some of the power and communication anomalies in scientific instruments. I remember there were a few times where something would go wrong in the instrument, and my mentor would go down to diagnose what's going on. I would go with him, and we'd try to like brainstorm and solve it together. But basically, the time I had at NASA Kennedy Space Center, absolutely amazing. I learned many lessons. The main lesson I learned in here is that the most important thing in an engineering job, in my opinion, is the people. And because I was in a room by myself with 8 very talented, very nice, very fun engineers, all working on this project, all part of this thing. That was just like the absolute coolest thing ever. It's probably up there as one of the most fun internships I've ever done, and the main reason for that was the people. Even though, like, as much as I liked the electronics and as much as I liked developing the PCBs and some of the analog circuits. Even though I was not very good at that stuff at the time, what I truly enjoyed is just being around smart, talented engineers, and that would plant a seed in my head where for the rest of my engineering career, I would basically be on a quest to find other smart, talented, like-minded engineers to spend time around and work with. Which was really, really cool. So that was the second internship. Again, the main lesson is find amazing people to work with. The main thing to look for in an engineering job is amazing people. And if you were interested in applying for something like that, I'm pretty confident you can go on the NASA. The way I applied for this, and I think it was called, I forgot what the program was called, NASA NIFS internship. Yeah, I mean, you could just Google NASA intern, and I'm pretty confident. There's Pathways, which is a different program, but then there's this intern program. And I think the way it works is, like, they list some projects, and you can just basically, like, start applying for the one you're interested in. Obviously, you have to be a U.S. citizen to work at NASA. And yeah, although when I talk about my next internship, which was at NASA JPL, things are a bit different. I think internationals can work there as well. So the next internship I want to talk about is at the NASA JPL. And again, I did that one when I was, it was 2019. So that was about 4 years ago. I think that was when I first started first started graduate school. So I had just went to Spain for study abroad, and I just came back. And my very first thing I did was I went to NASA JPL. And NASA JPL was this very, very cool place. It was like Disneyland for engineers. It's just amazing place. It's really cool. It's like in the middle of like the mountains. It's like its own campus. I have a picture right next to this thing. Yeah, like people would commonly pose like this, and I've definitely taken a few of these myself. And when I was here, I was working on a control system, and at NASA Kennedy Space Center, I was working on controls a little bit as well because it was involved in the hardware in the loop. But in this case, I had to work on developing a control system, and what I was trying to do is I was basically, let me see if I have some of my nope. So what I was doing is I was working on a control. Here, let's look at PID controller. So basically I was developing some type of control system where you have an input and you have, here, it's probably better I explain this visually. So what I was doing is actually right behind me over there, not the Arnold poster, but do you see there's that white little device over there where I'm pointing? That is a thermostat, and the way that thermostat works is you set a certain temperature and you tell it, hey, like I want it to be like 70 degrees or 80 degrees all the time. And then what it's doing is it has a sensor, and the sensor is constantly reading like the room temperature. And then if it's like too cold, it will put out heat to increase the temperature. And if it's too high, it will push out cold air to bring that temperature down. I was basically doing something very similar, but instead of doing it for a house heating system, I was trying to do it for this very cool balloon-borne telescope, and is a CO2 NASA JPL. So basically, the way, I mean, this was launched from Antarctica a while back. It was before I got there, and what they basically did is they basically take this telescope, they place it on this vehicle, and they launch it through a balloon in Antarctica. And you need to develop control circuitry that controls the current that is going through to the local oscillator in this case. And I don't want to get too technical here. It's a bit hard for me to explain these things, but basically I was developing like an automatic gain control system, which, like here, automatic gain control. I hope there's a cool visual here. So here, let's see if there's a simpler diagram. So this is basically a similar circuit for it. You're basically constantly measuring something, and you're adding gain to it, or you're subtracting from it to adjust it, just like the thermostat. And this was all happening at like devices that are like 240 gigahertz. I later also, oh my God, man, I don't want to get into the technical details of this, but basically, this was all happening at 240 gigahertz. I'll show you guys some paper. It's going to be a little technical, but don't get too scared. Say 2 kilometer motor. We're not. I can't type. Say less. Yep, right here. So part of what I was doing as well is I was characterizing something right here. Okay, so there are these electronics over here, and these guys right here especially, these were developed at NASA JPL. They're developed by my mentor, and we had to characterize these things. We had to plug them into oscilloscopes and power meters and basically make sure that they're performing properly. Now these things are operating at 240 gigahertz, so again, very, very high frequency. And the way we do that is we start with a local oscillator, we multiply until we get to the 230, 240 gigahertz. Again, the reason why you would ever go to the reason you would ever go to frequencies that are very, very high is because you want to have higher bandwidth, which will allow you to have higher data rates. So the quest with communications, and especially a lot of things I'm doing for my PhD, the goal really revolves around get to the highest data rates possible. And the way we do that is we go higher up in frequency. We go up to like 100, 200, 300 gigahertz. Some people in my lab are working on like 1 terahertz, 2 terahertz, 3 terahertz. It's crazy stuff. I tend to hang out in the 200 gigahertz range, mostly because that's also what makes sense for use in space. And I'll make a separate video on what I'm doing for my PhD and how it relates to some of this stuff here. But overall, the experience I had at JPL was very, very different, because while at the NASA Kennedy Space Center, I was in a group of 8 engineers. I was an undergrad. At NASA JPL, I was a graduate student, so I was expected to be a bit more independent, and I had 2 mentors and a group supervisor and a lot of other amazing engineers that I could like talk to and ask questions. But this internship was really more intense in that I basically had to it was independent work. I had to do everything myself. And majority of the days in the internship, I would basically be in this little lab by myself, figuring out how to make the automatic gain control circuit work, figuring out how to make the control loop work. And this was one of the biggest lessons I learned while I was at NASA JPL is you really have to be like you really have to learn how to solve problems independently. So it's actually a really nice contrast to my experience at Kennedy Space Center and my first internship at Northrop Grumman, where I was basically always surrounded by people and was always able to like bump into people and brainstorm things. This experience was a bit different in that I had to figure a lot of things out independently, which actually served as excellent training for my PhD, because later on I would go to my lab back in Boston, and then I would be doing my PhD in electrical engineering. And a PhD, by definition, is independent work. You're on your own. Sure, it could be collaborative, you could be talking to some people, but at the end of the day, you have to publish papers by yourself, and you have to come up with ideas by yourself. And you have your PhD advisor who you could talk to and bounce ideas off, but you meet maybe once a week, maybe once every 2 weeks. And again, you're kind of on your own. So that prepared me really, really well for it. Now, the other nice thing about NASA JPL is that there's a lot of international people that you could meet. So I met people from like France, Italy, Spain, people from like really all over the world. Some people from Argentina, people from Egypt. There's amazing scientists I met from Egypt. Like from, I don't know, South Korea. There's people from all over the world, and that's because NASA JPL is owned by Caltech. It's actually a private institution. It's a federally funded research center, unlike NASA Kennedy Space Center or NASA Johnson, which are owned by the U.S. government. But anyway, not to bore you too much with that detail. So that was that, and then basically, my very next internship after that was at Northrop Grumman, and I actually interned there a second and a third time, where here I worked on error control, and here I worked on atmospheric turbulence. And I'm gonna go over these two internships briefly because they were very similar. This was like post-COVID. I was at home. I did both of them remotely. So with error control, what we really are interested in is when we are sending signals, and this gets a bit into like information theory, ones and zeros, is whenever you're like sending information. Well, I think the pictures are just gonna be a bit more confusing. I'd rather explain it visually. So when you're sending signal from like, or any type of information from point A to point B, assuming that the signal will always get there without errors. Actually, a much better example. Let's say I'm talking to you right now, and my mouth, there's words coming out, and that's information, and it's coming to your ears. And because I'm talking very loudly and comfortably and slowly right now, you're most likely receiving and processing and understanding everything that was going on. But the problem is if I start talking really, really, really fast and you probably don't even understand what I'm saying at this point, like now some people might not be able to fully comprehend that, and you might lose some of the words and you might lose some of the information. So now one option that you could tell me to do is say, hey, Ali, can you repeat that? And this is called an automatic repeat request, I believe, where basically when you lose, like when you send a message and it doesn't get received or processed, you basically tell the sender, hey, can you send that again? That's one way to do it. But there are much more clever ways to do it, where you can rearrange the ones and zeros in the messages in a way that is robust and redundant, such that when you do get messages on the receiving end, you're able to decode them. It's a bit intense, but basically it's an entire process revolving around being able to send like forward error correction. Yeah, there's some way to explain it. So you basically have the data, you basically arrange it in a really, really cool, fancy way, and then the data gets transmitted, and then you decode it out of that really, really fancy way. And basically the whole goal of that, of error control, is to reduce the number of errors in a signal. And I probably have some bullets over here. So yeah, error control. I compared something called polar codes versus LDPC, which stands for low density parity check. And I was doing that for the VS2 standard, which is commonly used for like broadcasting satellites. I'm not really gonna get too much into that detail, but all you need to know is that for this type of internship, what I was working on is we have this signal over here from a satellite trying to come to the ground, and we want to arrange that information in a way such that by the time it reaches the ground, we have the least amount of errors possible. And if we do have errors, we want to be able to decode what the errors are, filter them out, and basically extract the information. This is a really intense internship. It was definitely out of my comfort zone, but it was really, really good because it forced me to learn new things, and it forced me to like be a beginner again in a topic I had like absolutely no clue about. And again, it was like very independent. I did have a team. It was remote, so that kind of made things a bit difficult, but I had, again, the engineers I worked with were absolutely amazing, absolutely helpful people. And yeah, the main lesson I learned from that internship is as an engineer, especially early on in your career, I think at that time I was only 23 when I did that internship. Do not be afraid to work on something new. I was branding myself as a hardware guy, and I'm like, oh, I only work on antennas and electronics. And then I got this internship opportunity, which was on error control, and I thought it was pretty cool, and I jumped on it, and it was completely out of my comfort zone, but I still jumped on it. And this is something I notice a lot, and people I've observed to be really good engineers, is if they see an opportunity that they like, they don't ask like, am I qualified? They just say like, yes, I can do it, and then they go figure out things on the job, and they learn things on the job. This was actually something I learned from one engineer I met at NASA JPL, where he would say whenever they assign him a problem, he would say, yes, I can do it, and then he would be like, in his head, I have no idea how to do this, but then he would go read about it, he'd go learn about it, and when you put yourself through that kind of pressure, you actually tend to learn how to you learn how to solve the problem, and you learn how to get over it, and you find the right resources, and you figure it out step by step. It's really cool. That's definitely the approach I took always, especially when I was in college and undergrad. I would always jump into things that I had no idea what they are, and the pressure of needing to deliver in a short period of time on something that you don't understand, like something kicks in you, like it raises your norepinephrine levels, your adrenaline levels, and you're just like, oh man, I gotta figure this thing out, and then you go ahead and figure it out, and it's very, very cool. Now later, the summer after, I worked on something a little different. It was basically, I was working on atmospheric turbulence, and basically, I hope there's a cool picture. Yeah, so this is probably a good picture that describes it. So basically you have a laser that's transmitting like electromagnetic waves that are in the optical range or infrared, like visible optical or infrared, and they're going through air molecules, and because they're going through air molecules over here, there's going to be some distortion of the signal, and by the time the signal is received, it's not going to be as perfect as when it was transmitted, and then you would need to use some type of lenses and corrective like methods to basically like reconstruct that signal at the receiver. So all what we're really trying to do with atmospheric turbulence, and this usually happens for lasers. This is because of a phenomena called scattering, and a little bit of absorption as well. Basically, when the wavelength becomes really, really small, so at optical frequencies, so optical waves or lasers, the wavelength is really, really small, which means you start interfacing with the molecules in the air and other things. That's why, for example, like a laser cannot go through like your hand, most likely is going to block it, versus like something else like Bluetooth or Wi-Fi or some longer wavelength will go through your hand. If again you're like very overwhelmed and confused by what that is, don't worry, you would learn about it in like either Physics 3 or Communication Systems or Electromagnetic Physics, depending on what class you take. But basically my job was to come up with a model to figure out different types of turbulence, and based on these types of turbulence, which mathematical like approximations we want to use. And again, that was a really, really cool project, because I worked with a bunch of people also on, and in this case, this was more of a physics project, because I wasn't really building any hardware, I wasn't really doing much, in terms of actual engineering or technology. All I was doing is trying to understand the propagation effects of what happens when the laser goes through the turbulence. And that was really, really, really cool. Again, this internship was also this internship was also remote. And the main lesson I learned from that internship as well is, as an engineer, you need very strong physics background. And very, very often in engineering, because engineering is the application of physics, it's like applied science. You might get lost in the idea of only wanting to do things that are hands-on, and you kind of take more of a technician's approach, where you become like only a tinkerer and learn things through trial and error. But in that internship, I learned how important it is to have like very, very good theoretical knowledge of physics, and how like a really, really good engineer understands the very basic physics that govern all engineering phenomena, especially, for example, in the case of electrical engineering, like electromagnetic waves. You really need to understand electromagnetic waves, and you need to understand the approximations that have, like how the behavior changes as the wavelength changes of the electromagnetic waves. And yeah, that internship was just very, very cool, because I'd worked on lasers before, but I had not worked on like the propagation effects that take place with lasers. And yeah, it was just very, very cool internship. And the last one I want to get over today, or I want to talk about, sorry, I'm like a little bit tired, but this was the MIT Lincoln Lab, and this was a very, very cool internship, because I worked on VLF antennas. And if you don't know what VLF is, it's very low frequency antennas, which, I mean, some of them look like this. They're basically very, very long. They're very, very long antennas. And here, let's see if there's I want to show you. Some of these are like a kilometer long. And basically you're going to VLF. VLF stands for very low frequency. And very low frequency is basically 3 to 30 kilohertz. Now, 3 to 30 kilohertz is very, very low frequency, which means it's very, very large wavelength, which means the wavelength is like is massive. It's like from 100 to 10 kilometers, the wavelength. So these are mostly used for like very, very robust communication, like very long distance, obviously need to say. But if you have taken any class on antennas or electromagnetics, you know that in order to excite a wavelength that large, you need an antenna to be like at least like a quarter the size of that wavelength, for example. In that case, a monopole antenna or quarter wave antenna. So what we would have to do is we would have to like design and build like an antenna that was basically a long cable and deploy it from like a helicopter or a drone, and then have some receiver on the ground that is like much smaller, because the power was really high, and even though the antenna was not very efficient, you're still able to capture a lot of the signal. And yeah, it was just a very, very cool project. I can't really talk that much about it because that one was yeah, it was a cool project. And working there was also really, really cool. Everybody there was like super smart. I needless to say, it was a subsidiary of MIT. So everybody I met there was like really smart and very, very nice people, amazing people. And I spent the entire fall semester working there. However, because it was not very much related to my research, I was working on terahertz for my PhD, while this was VLF. So I was going from very, very high frequencies to like very, very low frequencies, and that gave me a really good understanding of all the physics involved when the frequencies get really low. But the main lesson I learned from that internship was, like, early on in your career, you want to jump around and you want to like learn as much as possible. And this is something I've been very fortunate about, in that I have always been able to work on different things. I've been able to work on different parts of the electromagnetic spectrum. And like, for example, if we take a look at the electromagnetic spectrum, so I'm very lucky. I've been able to work on these guys, these guys, these guys, and these guys. Basically, all the different waves that you could communicate information through. Obviously, we can't really use these guys to communicate for obvious reasons, because they're going to kill you. But we, as much as that was cool, like in my late teens, early 20s, I turned 26 during that internship, and that's when things kind of hit me, when I said, like, man, it's cool to like explore a lot of different things, but I'm at the stage in my career where I'm nearing the end of my PhD, and I really need to focus on what I'm good at and what I'm genuinely interested in, and that is like terahertz and sub-terahertz communication, and basically being able to send information through space at 200 gigahertz, 300 gigahertz, 150 gigahertz. That is the thing that I really want to have a serious like chance at doing, and this was actually like a very painful lesson that I had to learn, because like growing up, I've always been interested in learning about many things, and within engineering, I'm so interested in learning and doing many things. But there comes a time where you need to learn how to focus, and you need to learn how to sacrifice some of the things you're interested in, so you can get like a really good and deep understanding in a thing that you're trying to do. So the lesson there is, if you're like very young, and if you're just starting something out, you should jump around and bounce ideas and get into as many things as you can. And it also depends on your definition of like young, like how young is, or how old is. I think, like, I don't know, like from a practical perspective, I think by the time you graduate a PhD, you should be really good at like one thing. And sure, you can be good enough at like few other things, but the lesson I learned there is there comes a time where like it's cool to keep exploring, but you really should put all your time and focus and energy into the thing that you want to be really, really good at. And you have to say no to many cool things in order to, and say yes to like few really, really, really cool things, so you can be really, really good at them. But nonetheless, obviously, in order to apply to either of these internships, I think you just go on their websites. I was lucky in that I think I applied like online, and then the recruiters reached out to me, and things just worked out quite nicely. But yeah, these are pretty much was basically a very brief and very fast, a little bit technical, a little bit messy explanation of some of the things I learned from my electrical engineering internships. If this was overly technical, I apologize. I hope you could maybe pause and look up some of these terms. I try to make these videos in a way where I'm just kind of like throwing a lot of information that I think is relevant. And if something seems interesting or sound interesting, I would urge you like pause and look more into it. And also a huge shout out to the Dazzling engineers, the Discord server, our Discord server, because this video topic was actually chosen by the engineering students in the Discord server. I will put a link for it in either the comments or the description or both, so that way you can, if you're studying engineering or you're curious about engineering or you're just interested in engineering in general, you don't have to be an engineering student. You can join us in the Discord and you can vote on the next video topic. I'm going to be testing that out, see how it works. But yeah, until then, I will see you guys next time. Peace, love.